some number, like a WVU gave you a student ID, U800 ID, is the same thing for the bacteria, okay? Just from a different perspective. So that's an example. The second example, Streptococcus pyogenes has M protein, which is M antigen from the cell membrane system. Therefore, based on Rebecca Lansfield group, Streptococcus pyogenes is group A Streptococcus. And we also mentioned about the Streptococcus ammoniae. There is no group. Is that right? There is no Rebecca Lansfield group. Why? Because Streptococcus ammoniae, there is no M protein. So that's a reason. That's something we can talk. Lots of the time, we also heard about E. coli. K88, remember? Now what this means? That's a capsule. That's a capsule antigen. So this is a very good example which tells you a whole body is not an antigen, a certain structure is an antigen. Very typical is flagella, capsule. The protein from the cell membrane system and LPS side chain, especially the H flagella and the LPS side chain, determined lots of the ID for E. coli 0157 for E. coli, including E. coli 0157H7, and we talk about the big six. Remember we talk about big six, 026, 0113, 033. That is also categorized by serological typing of the O antigen. But H antigen at this moment, we just skip that. We don't do that too often. Okay? So that is what we talk about. Now, since we have an antibody antigen reaction, okay, now what they really talks about, how they reacted with each other. There are 5 different possibilities or most likely ways they reacted with each other. What are the 5 different ways to do? Number 1, very simple precipitation. Precipitation, which means usually it's a small soluble antigen and antibody. It's a small soluble one. And they could be reacted, cross-linked, and then reacted precipitation at the bottom of the tube. If you do the centrifuge, it's a small soluble one, so that's called precipitation. If it's a large one, what's going to happen? Agglutination. It will cause cross-linking clumping. This is what we talk about in the lab exam. When we test Staphylococcus aureus, there is a way to do testing. What is that? Right here, on the top. So we have these called the Ramo disc testing paperboard. We put 1 drop of the reagent, which is antigen, and another is a bacterial sample, then we mix it. If you see those clumping right there, look at those clumping, which indicate antibody-antigen reaction, we call it a agglutination. And these type of thing, we call it a latex agglutination. And this is a latex agglutination kit is the easiest way to testing Staphylococcus aureus. That's why in the exam review I said a special identification method for Staphylococcus aureus, the best one is actually latex agglutination kit. Now of course coagulase test you can do it, but this one is a better one, okay? So this is number 3. Number 2. Number 3, what we do? Neutralization. What is neutralization? Antitoxin, the same thing. Same as antitoxin, okay? So you basically, it's just specific for virus. So antibody block the binding and they combined it, is neutralized. So these, the picture right here, these three are easy to understand. Now what are the other two? We already talked about opsonization. Lots of the time in your body, you rely on antibody and antigen is not enough. So let's say you have an antibody for certain microorganism. There is a certain microorganism coming. Then they reacted with each other. It will not cause precipitation, agglutination, and neutralization. What going to do then the body? The body going to bring somebody to help. That is the macrophage. This is one of the components of white blood cell, we already said. Then the macrophage will be migrates, go to the FC section, and then they help antibody-antigen reaction to destroy it. So which means I'm going to attack you on the top. You are originally going to work on the top. I'm going to attack you at the bottom. That's the way you do to curing the foreigner, curing the infectious agent. So that is called opsonization. Now, if the opsonization is not enough to do, what are we going to do? The last one. So opsonization number 4. The last one is really you have to do everything from your body is called complement fixing. What is a complement? This is a small immune active protein in the blood salient. And basically you have a C1, C2, C18, C25, blah, 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 a lot. These are the very immune active protein in the blood salient. They have to activate it to lysis the bacterial cell. And usually is you have a multiple different smaller antibody antigen complexed, and right in the middle is the complementing will be there to fixing it. So it's a lysis the bacterial cell. Okay, so antibody antigen reaction, actually there is a five different type. Now we're gonna go briefly talk about here. These days we talk about vaccination all the time. We already mentioned it. So what we have to do, it's not enough for our to do the natural defense system, physical barrier, white blood cell, antibody antigen. You can't rely on the rest of your life said, oh, I'm going to recover from one disease. Is that right? Then generate antibody and then they survive. There's no way to do. So what we have to do, lots of the medical companies, they generate which is called the artificial acquired active immune. It's a vaccination. So what are the vaccination? We just mentioned it right here, but we have a slide, we can go over it. Kill the microbes, polio, whooping cough. This is caused by Bordetella pertussis, if you still remember. This is not really effective. Sometimes kill the microorganism or microbes very short period of time, so need a booster. But attenuated is really good. Attenuated basically is actually a cell we heat injured, but it's still there, and I mean the bacteria still survived. So Sabin polio vaccine, MMR, is attenuated vaccine. We sometimes could do purified antigens. What means purified antigens? Which means you could be isolate a certain part from the bacteria cell wall to take it out, then become a vaccine. So meningitis, remember we call it a type B meningitis. It's a type B Haemophilus influenza. That is coming from the cell membrane system of the Haemophilus influenza, then become a meningitis, it's HIV virus vaccine. Whooping cough, we also could make that one. Toxoids, we just mentioned the tetanus, diphtheria, which is a DTaP, is a good one. Genetically engineered hepatitis. By the time when I teach this one, we haven't come out of coronavirus, so S protein is another one. But S protein, you also could be put in the categories purified antigens, because that is a protein, because it's an antigen from the cell membrane system of the coronavirus. So you take it out and you make a vaccine. Okay, so that's also a purified antigen, one of the examples. This one we talk about all the time. In the United States, recommended by CDC, vaccination of children begin 2 months. Okay, so you can see, typically DTaP, 2 months, 4 months, 6 months, you need different shots, we call it a booster, because the DTaP only active T cell line, they are not active B cell line. Same thing, HIV, Haemophilus influenza type B, pneumococcal ammonium PCV vaccine, which is coming from the capsule, which is coming from the poliovirus. The MMR basically is only 1 shot. Varicella is only 1 shot. And don't forget the last one. Meningitis, MCV4. This is actually could do later, but lots of the places they do at the first. But not many places they do. I don't think in West Virginia and Pennsylvania they do that. Pretty much all the newborn baby in this area, we're only going to focus on right on the middle. Those 1, 2, 3, 4, 5 ones is important. Is that right? You go to kindergarten, you go to primary school, they all require you have the immune recording. That is what it is. Okay, now, using the immune response, we also could do some of the diagnosis. And so, first of all, what is the serial? Let's say this is the blood. Okay, the blood we can do the centrifuge because of the platelets there. So after blood, what's going to happen? This is the blood cell. A red blood cell at the bottom, agglutinated. At the top of these light liquid is called the serum. And this serum, lots of the time, have many amounts of the, huge amounts of the antibody. So we call it an anti-serum. Now what means anti-serum? We can say it's a serum-rich, one type of the antibody. So that's what I just want to tell you. Let's say if some people just recovered from Streptococcus pneumoniae, you get a blood cell from the patient, you can be doing the centrifuge, and the top of the blood serum, that could be injected to some of the healthy people, and then they can be protected. Remember, before the coronavirus vaccine comes out, there is a very short period of time in certain countries, they do the protection. Is they get the blood serum from the patients, they do the centrifuge and purify that, then the blood serum could be injected for the people and to do the curing and also for the protection. Is that right? A very short period of time. But people find that it's not very effective. But so later on they developed a vaccine. Although there's lots of debate behind that, whether we should do it or not. But anyway, that's kind of the progress for protect ourselves. So here is the thing. This is the example, the last slides we talk about is the latex agglutination test, how they did that. This is a con. This is coming from, originally is from a rabbit. So usually they're using a rabbit as an experimental animal to generate antibodies and anti-serum. How they do it? They give a shot of heat-injured bacteria. For example, Staphylococcus aureus. The heat-injured Staphylococcus aureus go to a rabbit. The rabbit will not die. It will stimulate the immune response when there is a real Staphylococcus comes out. So they will generate kind of like an anti-Staphylococcus aureus serum. Now how we do it? We dig a hole from the ear to get blood from them. And then what we do? Centrifuge. When we do the centrifuge, we got from the top, we get a serine. This is what we call it anti-Staphylococcus aureus serine. And then we want to see the titer of this antibody. So how we do it? We use a microplate to do a serial dilution. It's a 20-fold or 10-fold serial dilution. Same like we did in the lab. And then we're going to add a Staphylococcus aureus. And we shake it. Let's be there, stay about 4 hours. We want to see which tubes at the first time showing clumping. If they show the clumping, the first one we took it out. We recorded it. And the reciprocal number of the dilution is a titer. So for example, right here, we see the first tube comes out showing the clumping is 1 divided by 160. Therefore, the titer of the antibody is 160. Obviously, the titer has to be the smaller, the better. Is that right? We want to be diluted more, we still have a huge amount of the antibody. However, I want to tell you one thing. Back 25 or 30 years ago, these type of the research are very difficult to do. What's going to happen? The rabbit is there. You give them carrots, you give them other things to eat. Once you generate an antibody, before you generate, the rabbit is already died. I just want to tell you, because sometimes the rabbits cannot survive that long period of time. It's keep you doing the immune stimulus. So that's a very difficult to do. The amount of the Staphylococcus aureus, how many you should be injected, it is difficult. So that is lots of the time. In the 30 years ago, this is a PhD dissertation to generate an anti-serine. And I want to tell you, when they just come out, how expensive it is. 1 microliter is $20,000 by the time. This is enough more than the WVU institution for a year. So that is very difficult to do. What I'm showing you here is just a demo. It is not really you have a rabbit, you inject it with heat, injured Staphylococcus aureus, and 3 months later you're going to generate the Staphylococcus aureus serine antibody. Is not really. So the rabbit is died, then you have a new rabbit coming. So what do we have to do? We have to adjust the amount. Sometimes, and also the opposite direction is the rabbit is survived there, but the rabbit did not generate any antibody. Or the antibody, the titer is very high. For example, lots of the time you get like 1 divided by 20. We don't want it because it's too high. So what we have to do, we need to give the injection of these things, of the complement. And sometimes we also have to give them IL-2, lactoferrin, all those type of the immune stimulates chemicals to let the rabbit to more reacted for the injected Staphylococcus aureus. So just I want to make sure you're understanding. These days, we get this kit is about $100 for like 50 samples. 30 years ago, that is very expensive because it's very difficult to do the animal experiment to control the dose will be appropriate to generate an acceptable titer. And this titer usually should be at least more than 100. If you get like 10, 20, 50, that's just too high. That means you need much more rabbits. Is that right? So that's not reasonable to do. That's why these things are difficult to do. Although we do here, it is easy, couple of slides. It took 2 years, 3 years to complete the experiment. Okay, so that's all I have for the immunology section. And we left one will be on next Tuesday. We'll talk about the virus, and we're also going to do the final exam review. Okay, and this Thursday there is no lecture because we had a final exam. And the first lab starts 11 o'clock.